Hey everyone, welcome to Cassandra Lunch number 103. We'll give everyone a couple more minutes to join and we'll get started soon, shortly. Hey everyone, welcome to Cassandra Lunch. We'll go ahead and get started in a minute or two, just letting everybody come in. Alrighty, let's go ahead and cut the music. Okay, hello everyone. Thank you for joining us for Cassandra Lunch number 103. If you're watching this live on YouTube, don't forget to like and subscribe and also turn on your notification bell so that way you can get notified whenever we do go live or we post a new video. Today's talk is going to be on Cassandra Cluster Architecture in UML, as well as the Azure Digital Twin domain language. Today's talk is going to be given by Nicholas Brackley, who's an enterprise architect here at Anant. Coordinators for this event are Rahul and myself. If anyone is interested in giving a talk at Cassandra Lunch or Data Engineers Lunch, feel free to reach out to me. My email is listed below, as well as if you're interested in sponsoring Data Engineers Lunch or Cassandra Lunch, you can reach out to me as well. We are a part of Data Community DC. Data Community DC believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect the respect to be given to all. Data Community DC is built of a bunch of different organizations. Our sister launch, Data Engineers Launch, falls under Data Wranglers DC. If you're interested in all the various organizations under Data Community DC, you can check out more at datacommunitydc.org. So what do we cover here at Cassandra Lunch? We cover everything that is Cassandra, talks Cassandra, plays well Cassandra in the ecosystem. So for example, open source Cassandra, enterprise like DataStax, Scylla, or managed or variants like Yugabyte, Cosmos DB, Amazon Key Spaces, as well as things in the ecosystem such as Airflow, Spark, Kafka. And so if anyone's new, say hi, hello. What do you do with Cassandra? What do you hope to get out of Cassandra Lunches? Or if there's something you would like to present at Cassandra Lunch. Group rules, if you have a question, ask it. This is meant to be community, so please do share what you know with us. But please do respect the speaker and be polite and courteous to others. The speaker will have their preferences and when they prefer questions, and they'll cover that when they take over. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. So Cassandra is our bread and butter. DataStax is a partner and a sponsor. GW University helps provide venue space when we have in-person events. We also have organizational and institutional sponsors. If anyone is looking for a job or has any jobs to offer, feel free to drop links, as well as if you have any hackathons, conferences, or classes you would like to promote, feel free to drop those links and we'll get them transferred to and from. We are hiring here at Anant full-time or part-time positions, data platform operators, engineers, architects. You can find out more at careers.anant.us. Upcoming events, Data Engineers Lunches happen every Monday at noon Eastern, and Cassandra Lunches happen every Thursdays at noon Eastern. Again, we are looking at having a more variable time slot, so that way we can cater to a worldwide live audience as well, but we'll keep you guys updated as we finalize those commitments. Cassandra Lunch, all these videos are available on our YouTube channel, youtube.com/AnantCorp, starting from Cassandra Lunch number 10 all the way up until today's Cassandra Lunch number 103. All available on our YouTube playlist, Cassandra.Lunch. Cassandra.Link should be your number one resource for all things Cassandra. All of these links are hand curated by the team here at Anant. If anything that is Cassandra or is about Cassandra or in the context of Cassandra, you'll be able to find some answers on Cassandra.Link. And we've also released our 4th run book. I will drop the link as of today. So this 3rd run book is now invalid. We will update it, but I will drop the link if you want to download our 4th run book that we've recently released, and we will drop that in the YouTube chat as well as the Zoom chat. And with that, we will hand it over to our speaker for today, Nick.
Thanks, Arvin. And I just want to say I've been working on these runbook projects sort of from their inception. And I think this is the best one that we've released so far. Very unified theme on documenting the resources that are and resource management associated with a Cassandra cluster. So my name is Nick Brackley. I'm an enterprise architect here at Anant. I have some formal training in UML, and I'm gonna share some of that with you today. My request for questions is that if you have a question, please speak up. I will stop and ask periodically if you have questions, but I generally think the odds are pretty good that if you have a question, you're not the only person that does. So please feel free to unmute yourself, and I'll do my best to answer. So let's start with architecture. The definition that most of us are used to is either that building thing or the conceptual structure and logical organization of a computer or a computer-based system. This is the very explanatory definition for how we use architecture sort of in our business. The definition that I learned that started resonating with me was shared by my professor, Ingolf Kruger of UCSD, and who's now working at Google. the makeup of a composite within context. So the makeup of a composite, I think a great way to think about this is to go back to one of the first wide-scale industrial composites that was built in the United States, and that is fiberglass. If you don't know, fiberglass is basically made by taking some fiber. At this point, we use almost exclusively carbon fibers. Take a bunch of carbon fibers that are hopefully relatively uniform in length and thickness, and then basically cover them in some epoxy, which is basically glue, and then sort of press it together into the shape that you need. So when you think about the makeup of that composite, it's not exclusively the carbon fiber, it's not exclusively the glue, it's this unification of the two. It's this combination of the different elements that compose a structure, that compose this fiberglass. And the within context part is important too. The ability of your carbon fiber, of your fiberglass to be useful is really dependent on what context it's in. If you are building a RV boat, that is a very different use case than if you're building a bicycle or a mega yacht that's designed to be a deployment base for a private military organization. So basically the context within which you're using the system that you're building, within which you're using your composite, is really important. And just to dive into the building example a little more too, when you think about architecture, it's not just the facade, it's also the plumbing and the way the electricity is wired and the feng shui, and all of these things together combine to be a system. And architecture is really about defining those systems. So in terms of industry standards for architecture, some of the most important types of architecture that sort of are these industry-wide definitions are functional architecture, generic physical architecture, and specific physical architecture. You'll see these represented in a lot of formal architecture frameworks like TOGAF or DODAF, but each one of these sort of serves a different purpose within your system, and generally they're built in this order, where you start with your functional architecture. This is a very conceptual system. So we'll look at a functional architecture for a Cassandra cluster in just a moment. But when you think about functional architecture, you're generally thinking about the concepts and the connections between them, the nouns and the verbs. The things you're going to get out of that functional architecture are the data that you're trying to manage. And if you're doing a really good job, you can even get the database definitions for whatever system that you're building. So generic physical architecture, the key term here is sort of physical, is we're starting to dive into what the components of your system are. And what the services are that are going to be hosted on that system. So generally with this service and component definition, we're thinking really exclusively about software, but a lot of architects will tell you that this service and component, these definitions can be extended to hardware systems as well. So the next step up in complexity is specific physical architecture. And what that means is not only have we defined what the service is, but we have chosen a provider for that service. We have figured out into what architecture, into what systems our services are going to be deployed. And the very last step in this, which, in terms of specific physical architecture, I almost think that a digital twin is moving towards a complexity level where it can be its own bullet here, is this idea of a digital twin. And we'll talk a lot more about what that is in a few minutes. So here is a basic functional architecture with something missing here. Take a look at while I'm talking and see if you can notice what's missing from this architecture based on what I just discussed. There are a couple things I want to highlight in this diagram. So first, everybody that works with Cassandra is familiar with this data center rack node structure. This is very standard for how every Cassandra system is built. Even if you have a simple 6-node, 10-node cluster that's in a single building, you still have to define your logical data center, your logical racks, even if this is just DC and rack. So some of the things I want to point out here, this is a bit of architecture education. We have these solid diamonds that in this case are connecting cluster and data center. What these diamonds represent is this composition relationship. This is saying a cluster is composed of, we have our multiplicity here for one or more data centers. Okay. So this is a really important relationship, this composition relationship. We have this open triangle here. In UML, this open triangle is usually going to be either a generalization or a specialization relationship. And just generally, that means inheritance. And the way you can sort of think about translating this open triangle is by saying the data center is a physical building. Regardless of whether that's a physical building on your premises or a physical building in the wilds of Utah, this is a reality of Cassandra systems. We have another composition relationship saying a data center is composed of racks, a rack is composed of one or more nodes. And now down in here in the node, we start getting some more interesting things going on. We have these sort of solid line, solid arrow relationships. This is the most generic relationship in UML, which is usually referred to as an association. And in sort of English language, we just think about this, this closed arrow being a has relationship. So a node has software, a node has data, a node has interfaces. Okay. And then the last thing we have going on down here is this association class with the dotted line and the solid arrow that's pointing to this association. And our association class in this diagram is a CRUD operation. And what that basically means is this is a verb. Association classes are almost always associated with methods, with things that are happening, but we're including them in this top level diagram because they are important enough to be included. Our node will have data that's changing. Our node will have software that's changing. That's the reality of the VUCA environment that we all operate in. And capturing that is capturing the environment as part of architecture, which brings me to my question. From our earlier definition of functional architecture, which is the makeup of a composite within context, what's missing from this diagram? What components are not included here that are necessary to really make this a good top-level functional architecture? Any thoughts? No wrong answers.
Well, if we're talking about context, maybe connections to the outside beyond the cluster.
Bingo. Yeah, there are no users here. There are no data sources here, right? There's one connection to context, which is this physical building, but that is exactly right, Obi. I mean, when you want a good top-level architecture, your system is never in isolation. And capturing the context that your cluster is working in is crucial to A, building a good architecture, and B, working with digital twins in the way that we'll talk about here in a few minutes. There's a note on this page that I'm going to come back to here in a bit. But first, let's finish this explanation of what these architectures are. So with generic physical architectures, again, right now we're not picking specific applications, but we're defining the services and the locations where they're going to be taking place. This isn't always 100% possible without getting a little bit more specific, but as much as we can, we want to try to define these generically. And there are a couple of benefits to this. Okay, the first and most important one, in my opinion, is this is fantastic for being deployment agnostic. And that's a big piece of Anant's framework, right? We are not tied, at Anant, we are not tied to GCP. We are not tied to AWS. We are not tied to Azure. We are able to operate within all of these systems. Part of the reason that works is because we understand the sort of structural components that go into a system. We're not saying the only search method is Elasticsearch, right? We know that there are valid service comparisons between these, and by defining the service generically, it's much easier for us to switch from one cloud to the next by just slotting in the comparable service into the specific architecture that we're dealing with. Generic physical architecture also does have some uses in training. I don't think it's as useful in training as the next specific architecture that we'll look at. But in general, being able to look at the sort of system as a whole is a really important piece of training or documentation knowledge for users in your system, and especially for administrators in your system, so that they can see the connections between your components and really see the system as a whole. Because as we all know, there are system level problems that can't be solved by expertise in a single component. And understanding the system as a whole is an important part of A, being a good architect, and B, being able to understand your system in its entirety. So are a couple sample generic architectures. Our one on the left here is really general. But when you look at a generic physical architecture, the thing you'll see that's different is basically boxes. You'll see these components that are defined and that are placed into a specific context. Okay, so our diagram on the right, we have our domains are our different racks, right? In our domain on the left, we have this big Kubernetes cluster domain that we're operating within. And we even have an API load balancer that's sort of reaching outside of this cluster that's helping us connect to the rest of the world. But then within our Kubernetes cluster, we have all of these other supporting clusters. What you don't see here, with the exception of Kubernetes and Cassandra, are specific choices for a cluster logging server. Like, we're not saying this is an elk stack. We're not saying this is Splunk and Grafana. Like, we are leaving this intentionally generic. There's an Airflow in here as well, but on the outside, we have a generic workflow server defined. This means that A, if we want to switch providers, if we want to switch environments, we can do that relatively easily by finding an incoming API manager that works on our system. It also means if we have a particular customer that says, I hate Airflow, we are never using Airflow, well, we can pull Airflow out of our design and slot another system that uses Airflow back into our design without having to dramatically change this generic architecture. And just one of the things that I learned very early on as an architect is, with these models, right now, our meta systems surrounding model design are not good enough to manage changing models easily. So one of the things in this 3-layer structure here is, if you're working with a specific physical architecture, if you're in this 3rd level of complexity and you have to change your functional architecture, there's a huge number of changes that waterfall down from that. And there's a huge amount of testing that goes back into making sure that the architecture which you've sort of built on top of your functional architecture gets all the changes it needs to still operate correctly. So key components of a generic physical architecture are no specific services selected, but generic services defined, and then this componentizing, where we're sort of defining the nodes, the systems that are going to hold our services. So by this point, you might be having an idea that specific physical architecture, this is about service definition. This is about making the choices that you need, and about defining the protocols that you're going to use to communicate between your systems. let's look at a couple specific physical architectures. This is a great Cassandra architecture. We can see that we have 2 Cassandra clusters here. And they're separated by this domain barrier. And they're separated also by this sort of functional definition of what the services do, right? We have this write-heavy Cassandra cluster, and we have this read-heavy Cassandra cluster. We're separating these in order to, or this analytics cluster here, I'm calling the read-heavy one. We're separating these because they're going to serve really different functions, and those functions are going to have different requirements on the system. We're also obviously selecting specific components here, and defining, paths of communication. If you were trying to take this and make it the next level of specific architecture, so if you were trying to add to the value of this architecture, what you could do is add specific communication methods. Okay, we're seeing some verbs here: backup, restore, patch, right? We're seeing some of these association classes, but what we're not seeing are ports or protocols. Okay, a fully fleshed out specific physical architecture is sort of like a blueprint for building a system. And with a great specific physical architecture, you can build a sprint plan that says, all right, first we have to instantiate our Akka systems, then we have to instantiate our Kafka systems, then we have to make sure that they're connected properly. And you have enough detail. You're not doing the engineers, the developers' job with this, but what you're doing is you're giving them a roadmap, and you're giving the project manager a roadmap that they can use to build your sprint plan, to build your basically to build the system that you're going to use to actually instantiate this architecture.
Yeah, Nick. And then one thing I just want to clarify here. I think it was just you misspoke, but referring to the 2 blocks with the Cassandra nodes, and this is actually I think you said 2 clusters. This is actually 1 cluster, 2 data centers that are synced, and that's what Cassandra does. Obviously, it replicates data across, and here you have Spark streaming, writing to write heavy, and then you have Spark batch on the analytics one as well, on top of that single cluster but 2 data centers.
Oh yeah, thank you, Arpan. That was a bad mistake. You can sort of see that reflected in the architecture up here, where the cluster is composed of these data centers. So saying that a data center has 2 clusters on it might be true, but those clusters are not sort of they're very separate elements that then have their own data centers within those clusters. Okay. So this data center logical piece, thank you for that clarification, Arpan. One more specific physical architecture that we're looking at here, just because I think this is a very well done diagram. Again, I want to highlight there are specific elements that are defined here. And there are containers, and I'm using this in the logical sense. There are domain barriers surrounding the elements which are connected, right? So we have Prometheus and Grafana working in a container within a Docker container, right? We have Elasticsearch and Kibana that are working in a much closer, more closely linked container than Grafana and Prometheus. There is some differentiation between those 2, and that is one of the main purposes of a specific physical architecture. So I think we're about to move on to digital twin. Here's another architecture here. This one I'm saying is semi-functional and semi-physical, right? This is a great image. This is a little bit maybe less of an explanatory. This is definitely not a formal UML diagram. This is a diagram to sort of show you a picture, right? And as long as your diagram is telling a story, there is value there. As long as it's telling the story that you want to tell. I'm calling this one semi-physical and semi-functional because we have our DCs that are split up between their functions, right? Our data centers are split up between their functions. It's definitely physical because these data centers are also, we have defined systems that are going to be working on them. Okay? And then the domain barriers absolutely make this a physical diagram. So we just went through a fair amount of content here in about 25 minutes. This is me trying to pass some of my education on to both our team and the larger community, because architecture can seem a little bit abstruse sometimes, and trying to componentize it, break it down, and tell you what we use each type of architecture for, I think has value. So I'll open the floor to any questions at this point. Okay, moving on. Let's talk about digital twins. First of all, digital twins are a very active research topic right now. You can find a lot of papers about digital twins. There are a lot of big companies that are starting to incorporate digital twins into their design process. While researching this talk, I found out that GE is really pushing digital twin design, both for their real-time grid management tools and for a lot of their complex projects, like building jet engines or building wind turbines. And we'll talk about why these two are great applications of digital twins. But first, what is a digital twin? So my basic definition here is it's a simulated system. But what it means is you are taking this specific physical architecture and you are adding degrees of reality to that. So for our Cassandra cluster, what that might mean is you're adding specific RAM, you're specifying your node. You're saying each node is a 8-core node with 60 gigabytes of RAM, and that your mem cache is a certain size, and you just get down into the details to sort of define your system. You can do this from the top level, or you can dive really deep. You can talk about how much energy is used per second of CPU use at a certain percentage of CPU, right? And one of the great tools that we're not going to get into today that's really useful for defining the physical side of a digital twin is a SysML, SYSML. SysML is a language that's been around for, I think, about 25 years at this point. I did a little work on it before I even graduated from my undergrad. And what UML is very conceptual, very top level. And what SysML does is it grounds models in physical reality. So it talks about, it has components for stress and strain on physical systems, energy use on electrical systems. Basically it's a great tool for incorporating physical reality into your system. But again, there's a lot of modeling that goes into all of these steps. One of the, why do we care about digital twins? And there are a couple of reasons, but I think one of the most important ones is it's great for testing. We ran into an issue that a couple months ago where we had a customer with a 500 node cluster. And I was thinking about how expensive it would be to recreate that cluster and test on it, right? We'd have to deploy all of that cloud architecture and then add huge amounts of data to it. Whereas a digital twin, we can run on a single node. We can run a digital twin on a single node. It's just numbers moving around. And we can use the simulated system to run our cluster through through scenarios. And that scenario language is one that you'll see used later when we get into the digital twin demo. One of the great things, another absolutely fantastic tool or application of digital twins is lifecycle analysis. And this is definitely a more challenging tool. This is beyond the level of sort of model definition that we're going to get into in the demo. A topic I'd be very interested to pursue in later talks. But what you can do with your digital twin is sort of make these scenarios move quickly, right? Once you have a digital twin built for a wind turbine, right? You're going to end up with scenarios occurring with that wind turbine that happen once every 5 years, right? You're not going to have hurricane force winds blow past your turbine every year, right? But what you can do is you can build your scenario in such a way that you can test this simulated system in a variety of conditions that are based on the real world. And that is the coolest thing about digital twins, and something that the DTDL does really, it appears to do really well, that I'm very excited to instantiate in a future talk, and that is connecting the simulated system, connecting your digital twin to telemetry from the real world. So what that would mean is your measuring devices, your thermometers, your humidity modifier, your altimeter, like all of the components, all of the actual measuring tools that are on your deployed wind turbine, right? You're pulling in data from that. Well, you can replicate that data and copy it into your digital twin so that you can see, A, how good is my model, right? Is the model reacting in the same way that the actual system did? And once you have a pretty decent, sense that your model is accurate, you can then replicate and slightly randomize your IoT data, this data that you've pulled in from all your sensors that are out in the real world, and you can run 10 years worth of simulations in a single year. This is obviously a big, complex task and was beyond my ability to produce for this talk. But this is sort of the end goal of digital twins. And you've heard me talking about some of these systems that use them a lot. There's a lot of investment that goes into building a good digital twin, a lot of good upfront investment. That's why companies like GE and even Bayer and huge GM, huge tech firms are using these to generate savings down the line and to create value for their stakeholders down the line. All right, so let's talk about these specific applications. We're going to switch gears here, and I guess before I switch gears, let's take a minute and open the floor for questions about digital twins. Does anybody have a question about digital twins? And I think if no one does, I'll spend a moment in talking about a Cassandra scenario for a digital twin here. Okay, so a great question was posed to me by a team member when I was working on this internally, and that was, there are already tools for testing Cassandra clusters, right? There are great, Cassandra Stress is a fantastic tool for figuring out if your Cassandra cluster can handle the load that you're placing on it. And that got me thinking about sort of A, how is a digital twin different from a basic stress test? And B, specifically, what are some of the things that you would want to test on a Cassandra cluster? Okay, so Cassandra Stress is like revving your engine, right? It's like revving the engine on your cluster. It's like figuring out, can the engine, can the pistons, can the axle manage the stress that we're putting on? Okay. What you can do with a digital twin is you can put it in a more complex variety of scenarios. Okay, you can define a scenario where half of the nodes in your cluster fail, or where you have an entire data center fail. Maybe there was an earthquake in Utah. Maybe Yellowstone went finally, and you can define these scenarios and see how your system reacts, see how much data loss you suffer. You can sort of look at lifecycle analysis, look at, as you get more data on your system, okay, what happens to the performance of your cluster? You can use that to sort of tighter to figure out when it's time to add new nodes, when it's time to remove new nodes, when the peak performance hours are, how long is it going to take you to bring those nodes up and down as your load changes. Just think there's a lot of potential for incorporating Cassandra systems or Cassandra Digital Twin as a training tool and as a research tool for how these clusters perform. Okay, so diving into our specific tool here at this Digital Twins Explorer. This tool was released relatively recently. It's currently only showing as available in preview on the Azure Marketplace. We'll talk about what that means. There are some really good things that it can do. You can import a variety of models. You can import whole ontologies, which is sort of when you think about ontology, this very definitional term, but it's sort of taking a glossary and putting it on steroids, adding the connections and the context to your sort of conceptual definitions here. So this is a very high-level application of modeling. There's a very easy graphical view, which is pretty nice. And there's a solid CLI that you can access either through a true command line and then API into your system. You can also, you'll see, we're just going to be able to sort of use the CLI in a graphical way. You can edit properties in real time, and you can use this connected to a couple of other Azure tools that we didn't get a chance to get into to connect your digital twin into devices in the real world. Okay. So there's definitely some value in this Digital Twins Explorer. Now, there are some issues as well. There are some modeling problems associated with it. Okay. The first thing here is that for some reason, they have defined all elements in their modeling language to be interfaces. I suspect this is so that you can add IoT data relatively easily to everything. It's just a sort of interesting choice. The digital twin domain language must not define any commands. That's because this is almost exclusively written in JSON. The language is very declarative, and trying to add domains in or add commands into your twin is definitely something that you might want to be able to do later on. You want to be able to do more than just change the scenario. You might want to be able to change the state in your digital twin. At this point, I think this is an area where they're going to be working on this pretty soon. One of the things that I found frustrating was there's only a single level of component nesting available. So basically, if you have, in our scenario, we had this 4 levels of component, right? We had a cluster, a data center, a rack, and a node. In DTDL, or excuse me, the DTDL, right? We're only allowed to have 1 level of component nesting, which means we can't say a data center is a component of a cluster and a rack is a component of a data center. This seems like a pretty arbitrary limit. I don't think this will stay this way forever. And it's just sort of an odd error that shows up from time to time. And also sort of this top piece here, and keep in mind interfaces is sort of every element in DTDL. You can define a lot of things within a basic model definition. You can define properties, you can define components, but you can't define other interfaces within a single interface file. What this sort of leads to is complex models are going to end up, you're going to end up with document creep, which is an issue with every modeling system. EA Sparks has this issue where changes in one model are going to affect everything. So does Visio. Like, this is just a problem in modeling, in the state of modeling in the world right now in general. But it's definitely a problem in this relatively young modeling language. I would also add that while the query language is very similar to CQL, it's not absolutely identical, and that there might be a small learning curve there. So we're going to go through 3 things here. We're actually going to skip the room and floor tutorial based on how much time we have left. But we're going to talk about this. We're going to talk about using Azure to start the instance. And then I'm going to show you basically some of the key components that we talked about: relationships, inheritance, and composition. I'll show you a short query example. Okay, so switching gears. Let's talk about this Azure Marketplace. I don't have time to tell you how to get certified on Azure. This was a process for me that was kind of frustrating. And this is simply a resource group. This is one of the most basic components of the Azure ecosystem. This one takes a little longer to spin up, so I spun it up for us beforehand. But basically, this is something before you start virtually anything in the Azure Marketplace, you'll have a resource built. And I just named it Digital Twin CL. This has nothing to do specifically with the resource group itself. So when we want to create a resource to put in this resource group, there's a nice search element here, which is going to let us find our component. Well, it's supposed to let us find our component. You basically are pulling from your service list here to find your digital twins. There we go. Now, there we go. So we can create this Azure Digital Twin. There are only a couple things to pay attention to when you do this. You can create a new resource group from this if you don't have one already, but I wanted to save us a little bit of time. So I'm going to select the resource group that exists. I'm going to assign myself the data owner role so that I can do a lot of the editing that needs to be done. And I'll just show you some of the options that are available. It's pretty easy to add endpoints and resources so that you can communicate with the internet. You can pull in data. Again, a lot of just easy things to do here. If you have a lot of Azure resources in play, I know tags are very important. You can tag by customer, you can tag by project, you can that sort of thing. Jira task if you want to get really specific. And oh, let's see. What did I miss? Oh, I forgot to name it. The resource name is Digital Twin Demo. And let's create it. What did I miss? Oh, not valid. 1. Cool. Somebody had already created one of these. So this is going to take a moment to deploy. While we're doing that, while it's deploying, let's sort of look over the model that I've built for this demo. So this model is built of 4 files, 4 JSON files. And this is based directly off of this structure that we looked at earlier, this functional architecture that we looked at earlier with cluster, data center, racks, end nodes. And basically, you're going to end up with a file for every class in your functional architecture. So there are a couple of things to pay attention to here. I'm trying to keep myself under time. This name up here, this ID is pretty important. Again, everything is going to be defined with an interface. This display name is exactly what it sounds like. And this context is sort of basic level tagging. You'll get very used to this structure with these 2 colons and the semicolon. So all this is saying right now is that we are defining this interface called data center that has a comprised relationship and this comprise relationship has a owner, right? What this is not doing is it's not specifically telling us with this language that's written here what the comprise relationship is connected to. In the language of digital twins, in the language of this digital twin, this is a, is it right here? It's right here. This is a non-targeted relationship. You can also define specific targeted relationships, and you'll see in a moment sort of what the differences are there. Nice. We're spun up. So in your this is the specific Azure Digital Twin resource that's been built on our Digital Twin resource group. Okay. Again, these are a lot of settings that you can manage: outputs, event routes, inputs. These would be very important for sort of the next level of application after this, beyond basic model definitions. There's definitely a bit to learn with basic model definition. If you didn't see, I just clicked on this Open Azure Digital Twins Explorer. I'm still expecting to see changes to this system moving forward. Right now, there are no models in my system, okay? It's totally empty. As you can see, both my model graph and my twin graph are blank. Okay. So some of the key interfaces on this UI are in model graph. Uploading a model and uploading a directory of models are definitely the two elements that you're going to use the most often. You can also just add images to sort of improve the visual appeal of your model. I'm going to pull in all 4 components at the same time here. We didn't get a chance to look at the other 3. We'll look at the node model here in a few minutes. But as you can see, all this does so far is it pulls in this generic picture of a class. This is saying there is a class that is cluster, there is a class that is rack, there is a class that is node, there is a class that is data center. And there are currently no relationships of inheritance or composition or generic association between any of these. And that has to do with what I pointed out to you a moment ago is, again, this is a non-targeted relationship, and so are all of the relationships in this demo, right? If I were to target these relationships, which, again, not super hard to do, it's very easy to see, there's great documentation for this tool, then even at this basic model level, we would be seeing arrows connecting these classes, okay? So the next step in this demo is we're going to now instantiate both the relationships and the properties associated with these components. Okay, so we're going to switch over to the twin graph, and we're going to import a scenario, right? And the scenario that we're importing here, this is just something that I've defined. We'll take a look at this file. And you'll see that this is basically a series of relationships that are defined here. This comprise relationship is defined as connecting the cluster and DC1 and DC2, defined as connecting DC1 and rack1, rack, etc. And then it's also instantiating some of the properties that have been defined, okay? And let's take a look at what properties there are to define. So there are a couple properties that are defined in, I believe at the cluster level. Oh, it looks like maybe that didn't incorporate correctly. We'll get to that in a minute. But there are some properties that are defined here. Software defined as a string, right? Data defined as a string in this case. And then here we have an interesting element. We have what's defined here is a specific unit. And this is really one of the things that tells me how Azure wants us to use this tool, right? Azure wants us to use this tool to pull in IoT data from existing systems because what they've done is they've given us the ability to get really specific about even the units that are associated with our measurements. So let's take a look. We're going to look at all of our elements that are in this twin. Ooh, there we go. So our output panel, where are you? So, let's see. So, that's the issue. So yeah, this has happened to me a couple of times. When you first import your instantiated model, you have to make sure that you save here in order to get your components. Yeah. So what I've just done is I have said, show me everything that's in the digital twin. Okay. And when I click on an individual node, we should be able to see here. Oh, let's see. There are a couple of nice options for viewing things differently. And some easy physical changes that you can make. This is clickable and editable. But again, notice that the model graph still isn't showing these relationships. That's because the model doesn't include the definition, right? It doesn't include the specific instantiated relationships. What the twin has done is it's taken the model and it's added both specific values of the properties and it's added these relationships. Okay, so we can look here. There are lots of options for viewing in a little more detail. So let's see. Yeah, I can't figure out what's going on here. That's going to be annoying. So let's see if this is going to work correctly here. So what I've done is I have edited this query so that I'm now still selecting from digital twins, but I'm now looking for the specific nodes where the percent CPU usage by the node is greater than 60%. Okay. So here we go. And notice it's highlighting node 1 and node 4. Okay. These are the only nodes where our CPU percentage is greater than 60%. So again, there are a lot of graphical low-code options for managing this. I get the impression that, again, this system is very much still in development. But for now, thinking about where you could go from here, okay? You could connect these nodes to actual nodes that are deployed in a physical system, right? And measure their energy use, measure their input and output rates, and get a little more complex with what's happening. But just generally, some of the things that I found interesting about this exercise were first getting your sort of values here, getting to this output where we can see this graphical display of our system. Took a fair amount of messing with these JSON files. Some of the annoying pieces had to do with making sure that the name of the relationship was exactly the same in both the relationship definition in your JSON file, right? So up here, we defined this comprise relationship. You have to use the exact same comprise definition in your instantiation file. Okay. There were a lot of little twiddly pieces to get right here. So I'm basically out of time. We have 1 minute left. Does anybody have any questions about this tool, specifically the ability to build models here?
No specific questions, but there was a comment from the YouTube chat that
Sure.
some other testing tools, like you mentioned, Cassandra Stress, NoSQL Bench is another one, as well as it looks like Gemini. I'm not as familiar with Gemini, but I've heard of NoSQL Bench as well.
Yeah. In general, I would say the most important use case for a fully fleshed out digital twin like this is a relatively large company that plans to invest, $50,000 in a project like this in order to for an existing system that they're trying to improve. That's probably worth $1 million or more here. This is definitely not a tool that every company needs to use, but it can make a $1 billion company $100 million richer if you use it right. And I was able to get the properties to display here on the right. You can literally edit these properties in place here, and notice that the software of our nodes with the high CPU usage have a standard stack and airflow. That's a nice little piece I wanted to share there. So we're at time. Thank you for listening to my talk. I'm happy to field questions offline. You can contact me through Anant. Very happy to be here. Thanks so much for y'all's time.
Alrighty. Thank you everyone for joining us for Cassandra Lunch. Don't forget, we've now released our 4th public runbook. It is now available. We've dropped the link in the YouTube chat as well as the Zoom chat. So you can fill out the form, get it for free. And with that, we will see everyone next week. Take care.